Everyone, this is the Introduction to Calculus peer-to-video. It's a class meant for students who've had some exposure to algebra and geometry and are looking to gain understanding of the core concepts of calculus and just learn a little bit more about the class. So let's get started. So first, a little bit more about peer-to-peer. First of all, welcome. We are a student-led free online peer tutoring program, and we connect mentors with students online through our group sessions, our one-on-one tutoring sessions, and more recently, our video platform. To stay connected, you can email us or follow us on social media, and we hope you enjoy the video. A little bit about myself. My name is Sherry, and I'm a rising junior at NCSSM. I took AP Calculus A, B, and BC, which is how my school does it, this year, and I really enjoyed the class. I thought it was really interesting. In my free time, I like coding, biking, and I'm currently watching Suits. I'm also the founder of Peer-to-Peer and the lead for the Peer-to-Video program. So I hope you guys get an understanding of calculus from this class and learn to love it as much as I did. So for a little bit of a lesson outline, first we're going to be going over the history of calculus, how it came to be. Then we're going to be talking about limits and continuity and the concept of infinity, which is a huge concept in calculus. Next, we're going to be diving a little bit deeper into one of the first concepts you'll encounter, which is derivatives. First from secant lines and then to tangent lines, the definition, and then talking about how integrals and derivatives play together. I'll be showing you the power rule, and then we'll be talking a little bit more about what you'll actually see during your course in calculus and the real-world applications, along with some resources that you can use to study on your own. For a brief history of calculus, calculus is the study of limits, continuity, derivatives, integrals, and infinite series. That's a lot of words that you probably don't know what they mean right now, but you'll come to know what they mean after taking the class and a little bit after today as well. The big idea for calculus is that it's the mathematics of change. So before, when your variables always had a fixed number, now they're always going to be changing, and sometimes at infinitely small intervals. So what calculus is a completely branch of math. You're going to want to leave a lot of what you've learned in algebra and geometry behind. That being said, you will still apply a lot of the concepts to calculus. So a lot of people say pre-calculus doesn't prepare you for calculus at all, and that's true to some extent, but you'll also be applying the principles of integrals and derivatives to different things that you've learned in pre-calculus. So it's a new type of math, but you'll be applying it to old concepts. It was invented by Isaac Newton, who you also probably know from his laws of motion, his work with a telescope, physics in general, and a man named Gottfried Leibniz. And they both independently discovered calculus on their own, and they're the founders of modern calculus. But before that, many other civilizations, Babylonians, Greece, India, had used the concepts of calculus to solve problems such as calculating area and speed of things that maybe weren't completely linear or predictable. Calculus has been around for a long time, but what Newton and Leibniz did with their modern calculus was Newton applied calculus to motion physics, which is his other branch of study, through things like particle motion, distance, velocity, and acceleration. And these are all concepts you'll be covering in your calculus class too. And what Leibniz did is he brought a lot of the notation that you'll be using. So I'll include the slides down in the description, and you guys can check out that video, which provides a little bit better of the history of calculus. So the first concept you'll want to learn is the concept of limits and continuity. And you probably touched on this a little bit in pre-calculus, but the first unit of calculus is generally a review of what limits and continuity are. Some things you want to remember is that infinity is a concept. It's not a number. It's not something that you can plug into your equation. And in that way, it kind of doesn't follow a lot of the rules that normal numbers do. So what you do for limits is you use them to approach something that looks like it's going to be undefined. For example, in this graph right here, you can see that it looks like f of -3 over here is going to be undefined because there's no value there. There's literally a hole there, and that's what it's called too. But if you try to approach f of -3 from the left, you can see that it actually does have a value, and it looks like it's about -2. So that's kind of the idea. This graph is actually really good for showing a couple types of undefined points that you'll see, or discontinuities that you'll see. Here you can see there's an asymptote at this line. Here you can see there's a jump. Here you can see there's a hole. And those are just some of the types of discontinuities you'll see. Here's an example of why infinity is a concept. If you look at 1 over infinity, you kind of don't know how to do that. You might think that it's 0, but actually taking 1 over infinity is like taking 1 over cat or 1 over some other word. It doesn't make sense. Normal numbers don't comprehend it. But if you take the limit of 1 over x as x approaches infinity, if you take the limit of that, you can start to see that it gradually gets bigger, like 1 over 10, it gets smaller when it gets to 1 over 100, 1 over 1,000, even smaller. And eventually, yeah, you do get to a concept that's around 0. So taking that same idea, I want you to think a little bit about what 1 over 0 might equal in the calculus world. Because before, we would see 1 over 0, and we would say, that's impossible, we can't do that. But now, it does equal something. And I want you to think a little bit about that. So another big concept in calculus is that if you add infinitely small pieces infinite times, you get a number. And that kind of makes sense. And that's what allows a lot of the estimates used by calculus to come about. You take something, you chop it into infinitely small pieces, you add it together infinitely times, and it gets you an approximation of the area or something. With limits, what you'll want to remember is that your end goal is to plug in the number. I think you do a lot of simplifying and trying to evaluate limits, and really what you're doing is just rearranging the expression until you're able to plug in the number. So even something like limit of x to the 1 of x plus 2, that looks really obvious, but that would be what you're trying to simplify to, and that would just equal 3. So now let's talk a little bit about secant and tangent lines and how that proves the definition of a derivative, which is what we'll go into in a second. From geometry, you probably learned that a secant line is just a line that intersects 2 points and kind of cuts your figure into 2 sections. So you can kind of see with this secant line right here, it intersects these 2 points, and it's just a line that goes through 2 points. It's not that deep. But you do want to keep in mind the formula for finding the slope of this secant line. Because essentially what a derivative is going to end up being is finding the slope of a line. So what happens with the secant line is the slope would just be rise over run, like we've always learned, and it would be f of x minus f of c all over x minus c. So that's what the slope of this secant line is. And you'll want to keep that in mind when we're trying to prove the definition of the derivative. So what happens when we try to take the slope of this tangent line that only touches the graph at one point? Well, we can't use what we did before with the secant line because we don't have 2 points to work with anymore. So what happens? We can go back to what we just learned about limits. If we can't take the value of something, try to take the limit of that value. And if you get infinitely close to that value, then you've just got it. So what we end up doing is we take the second point right here, and we're able to take the slope, which is the equation that we just came up with, and take it as this point goes infinitely close to the other point. So you can kind of imagine how this line would shift until here with these 2 points, maybe here with these 2 points, all the way until you've got this line right here. And then you would have the tangent line. So let's look at what exactly that definition of a derivative is. All right, so here's the definition of a derivative. And if you take a first look at this formula, it looks kind of complicated. You don't really know what to do with it. When I first looked at it, the thing that stuck out to me was h. Like, where did h come from? But let's kind of unpack it here with the help of the same thing we just discussed, which is secant and tangent lines. So I'm going to draw this random curve over here. And then let's do secant line right here. And let's try to define a couple lengths, because when you're trying to come up with a formula, it's always helpful to have variables. And I want to define this length between the 2 points of my secant line as h. And I can do that because it's just a variable. And then I think that's really all we need. So this is the x-axis, this is the y-axis. So if you take a look at this formula here, it's really just the same definition of slope that we just talked about. So the f of x plus h would be this length. The f of x would be this length. And this would be the x in this situation, since that's the point that we are trying to get the tangent line of. So the rise would be f of x plus h, this longer distance, minus f of x, this smaller distance, all divided by h, which is just the run over here. So that's the slope of the secant line, and now we kind of understand where this comes from. But why do we want to take the limit of h to 0? That's what we discussed before. We want the distance of this to be so little that the 2 dots eventually go to 1 point. So you can imagine how the dot would travel along the function until it just ends up here. And at that point, h would be 0, and we would have the tangent line right here. So that's just how the definition of the derivative, that's kind of an intuitive understanding to what a derivative is. I think in the first couple of units, you'll be plugging a lot of functions into this formula, which can be kind of annoying, but it's really to get to show you what a derivative is. And see if you can make sense of the alternate form of a definition of derivative down below, and see how it correlates with the graph that we just drew. So now that you understand what a derivative is, let's take a look at one of the first rules that you'll use when actually finding a derivative. So a big part of, I would say, the first semester of calculus is just learning different rules to find derivatives. You'll learn it for the various functions you've learned: polynomials, trig, logs, all the functions that you've learned, you'll learn rules for. And so the power rule is one of the first rules that you learn, and it's how to find derivatives of a polynomial expression. So what it does is it takes x to the n, as you can see here, and the derivative of x to the n is just n times x to the n minus 1 power. So what we did is we moved n down here and we subtracted it by 1. And this formula, I guess, is actually pretty easy to prove if you keep in mind the definition of derivative from earlier. So try to plug some common functions maybe into the definition and see what you get, knowing what you know about limits. So the power rule, you're going to use it a lot. It'll be second nature by the end of your course. And so I think it'd be helpful to just try a couple examples here and make sure you really understand it, make sure you know how to use it. And I'll put the answers to these below as well. So now that we've seen a little bit about derivatives, let's talk about integrals, which is something that we maybe haven't talked about as much, and how they tie together with derivatives. So if it wasn't clear already, a derivative is the slope of a tangent line. What does that mean? It means it's the slope of a line at one point. So for example, the derivative at this point right here would be that line, and that would be denoted by the notation f prime of x, as you can see here, where x is just the point on the x-axis this falls. F prime of x is the slope, the rise over run of this line. If the derivative is positive, that means the graph is increasing at that point. If it's negative, that means the graph is decreasing. And if it's 0, that means the graph has reached a maximum or a minimum at that point. And you'll learn more about this as well. But just to kind of give you the idea. For an integral, what an integral is just the area under the curve. And you'll see how this ties into derivatives as well, because this is the expression for an integral. If you go from the point A to the point B, the integral is just taking the area under the function for this whole length. And that lets you find area along with undoing an integral. So let's take a look here. So derivatives can always be calculated. They're generally easier to calculate with the formulas you're given, while integrals are a little bit harder. So when you're calculating integrals, you'll find that you're basically trying to undo the rules of derivatives. You're trying to use them backwards, which can be a little confusing sometimes. But all the derivatives you'll be given in your class, you'll be able to do as well. And the derivative is the slope at an instant, or the slope of the tangent line, while the integral is the area under the curve. The derivative of a distance is velocity, and the integral of velocity is the total distance traveled. So you can kind of see how they undo each other. If you take the derivative of something and then take the integral again, you'll end up back with your function. And that's really important to remember. So now that we've taken a little look at integrals and derivatives, and feel free to comment any other questions you have and I'll answer them. Let's take a look at calculus in general and what you'll be learning. So the first unit of calculus is limits and continuity. And that, again, just plays off of what you learned in pre-calculus about limits and gets you to kind of start thinking about infinity. With derivatives, which is the first semester of your course, you'll learn the definition of derivative, your various rules for finding derivatives. Make sure to study those a lot because you'll be using them for the rest of the year. So really get those in your head. You'll learn implicit differentiation, which is deriving in terms of a variable. And you'll see dy dx a lot there. You'll learn second derivatives. You'll learn how to find extrema, which are just maxes and mins. And like we discussed earlier, that happens when the derivative is 0. You'll also start thinking about calculus in terms of particle motion, a little bit like what Newton did before. You'll think of it in terms of distance, velocity, acceleration, and do a lot of word problems doing with that too. You'll get a lot of real world situations, probably situations that calculus wouldn't be used, and you will apply equations to it, which is what the AP test is on a lot as well. Your second semester, you start to learn about integrals, and you can see that they're basically reverse derivatives. With integrals, you'll learn to find average value, area, volume, polar and parametric. You'll also learn how to find rotational volume, volume of cross sections, and you'll see how to estimate integrals as well, using things like Raymond's sums and Euler's method. Other concepts you'll learn are infinite series, which is using that sigma symbol that you've probably seen before, and seeing whether those series diverge or converge, so whether they have a value or whether they end up at infinity. And calculus actually does play a lot into those series as well. You'll learn about Taylor series, which is a way to approximate functions, and the error bound of these approximations, since all approximations have an error. You'll also learn about differential equations, which is kind of ties into derivatives as well. If you're at a school where AB and BC calculus are taught together, you'll probably end up with a month or so to review the material. And you'll really do a lot of FRQs, do a lot of multiple choice questions, and make sure you understand how these concepts play together, and remember all the concepts that you've learned. So after you've learned all of these derivatives and integrals and whatnot, you're probably a little bit confused and asking the question, when will I ever use this in my life? Which we naturally ask with everything we learn. So if you're going into STEM, you're going to use calculus. You're going to have to be using integrals and derivatives to calculate things, especially if you're going into physics or engineering, things like that. If you're in school, other courses that you can take are AP Physics C, multivariable calculus. Those will meet your graduation requirement as well. And in college, AP Calculus will give you a calculus course as well. There's definitely opportunities to keep learning calculus in college. This link takes you to a really funny video, not funny, but really interesting video of MIT students who are still trying to find interesting integrals to solve. In physics, you'll use it a lot with kinematics, equations. And some of the equations that you learned that before you were just memorizing, they'll start to make sense once you learn calculus. With engineering, you'll use it with forces. With robotics, you'll use it with motion as well. And in economics, statistics, generally any STEM field, you'll be using calculus. And computer science is really helpful in machine learning and data science to try to find what the best solution is for a problem. And it's used in medicine as well. I've linked a great video for the applications of calculus. And here are some additional resources that you can use if you want to study calculus more in depth on your own time. Khan Academy has a great curriculum. They have one specifically tailored to AP calculus, I believe. And you can go in there, watch their videos, do their exercises, and you'll get a really good understanding of calculus. Eddie Wu is also a really good YouTube channel. He has an introduction to calculus series, I believe, that you can watch, and he explains things in a really intuitive sense as well. I've linked a couple more courses, along with College Board's AP review on YouTube. Since this year, they decided to release some digital curriculum that was really helpful. You can check that out as well. And then this video isn't calculus, but an overview of math in general. And I think it's really interesting to see where calculus falls and where all the other math you've learned falls in the entire field of mathematics. And the final thing you can do is request a session with peer-to-peer, where one of our tutors will sit down one-on-one and teach you whatever you would like, and that could definitely be calculus. So thank you for coming. I hope you learned a little bit about what calculus is, the basics of calculus, and I'll link a feedback form down below if you have any questions or want to tell us how we can improve, or if you want to make a peer-to video yourself. So thanks for coming. Welcome to Peer-to-Peer Charlotte, and I hope you learned something. Bye.